But he's not doing it. He's in like a miswriting work on that.
Yeah.
Yeah, like miswriting will just tell you to do the same thing.
So today we're going to talk about derivatives for polynomials, working with power rule. Happy polynomial, as long as it's a variable raised to an exponent power. It's much more efficient than going through the limit definition of a derivative. But again, the purpose of that limit definition is twofold. One, to show the connection between the slope formula and this new derivative formula, that we're able to achieve the exact steepness at just one single point, deriving from that slope formula. And the second reason is that we saw on Friday how an AP problem can be phrased in a way that requires knowledge of the limit definition of derivative. But now that we're past it, we're just going to be working with a much more efficient way of getting to the derivative, which also means that we can find the derivative of functions that are a lot more complex than the ones that we worked with before. Okay. And this is really, I would say, the foundation for the rest of the semester here. This is this power rule is a rule that we're going to use for all of our derivative section. But even when we get to our antiderivative later on this semester, this is also going to be needed. So if there's one rule that's the most important out of all the ones that we learned, this is it. Okay. So first, let me go through something called the constant rule. The constant rule says if f of x equals c, then f prime is equal to 0. So that means if a function is a constant, then f prime. We're always going to treat f prime like we can say slope, right? If my graph is a constant, then my slope is always 0. So for instance, if I have y equals 5, that is a horizontal line. That line is holding steady at a slope 0 the entire way through. So the constant rule says it doesn't matter what that constant is. If I can visualize a graph that is just a horizontal line, my derivative is always going to be 0 because the slope of the horizontal line is always 0. Okay, so power rule here, if f of x equals x to the n, then f prime is equal to n times x to the n minus 1. So the power rule, that's a much more efficient way to find the derivative than what we did with the limit definition, is we bring the exponent down as the coefficient in front of the variable. So we identify that exponent, we bring that exponent down. That's where that n comes from. Then we subtract 1 from the original exponent value. So if this is a 3, we'll bring the 3 down, and then we'll subtract 1 from 3, and we say 3x to the second power. Okay. Now, power rule is going to be very useful. It's going to be the one that you use more often than any other rule. However, it comes with conditions. There are times when we don't want to use power rule. There are times when we may be tempted to use power rule in in places that are either not ready for it or places that that cannot be used. So first is this is more of a helpful thing. We always want to convert radicals to rationals. That way we can clearly see the exponent in play. So for instance, square root of x to the 5th power is equal to x to the 5 halves. And then we can go from there. And I purposely chose this one because this is the one that gives students the most trouble. Because there's a hidden number here. What's square root here? That's a hidden what? 2, hidden 2 here. And we always do the exponent divided by the root. So it's 5/2. So a lot of times I see this issue here. I see students say this is x to the 1/5, which it is not. Or I would see students say that this is x to the 2/5, which this is not as well. So just be careful that this is the one that gives students the most trouble, because that hidden 2, and then typically we want to read from left to right. So that's why these happen, or we assume that that's a 1, but that's not a 1, right? That's a 2, right? If you forget that rule, then you know that you can use this to kind of help anchor your statement here. What is square root of x equal to? X to the 1/2. And if you ask yourself, okay, where's that 1 coming from? That 1 is coming from this hidden number to the right, and then that 2 is coming from that hidden number to the left. So if you can remind yourself, okay, if I know square root of x to the 1/2, where's that 1 and 2 come from? And look at the order that you're putting your exponent in. Hopefully that will help remind you in a way that you won't make a mistake with this form. Okay, so the second condition is bring the variable to the numerator before applying the power rule. So we cannot do power rule if the variable is in the denominator. Okay, it's got to be in the numerator first before we apply power rule. And the third is expand your terms. Resolve your parentheses and your fractional terms before applying power rule. If you don't do this, then you run the risk of getting that the derivative incorrect. Okay, so make sure you resolve parentheses. An important note, be sure that function is in appropriate form. Make sure all conditions are met before you apply your power rule. Okay, so we'll start with some easy ones, and then we'll kind of build up to the ones that are more involved. So y equals x to the 7th. Everything is ready. There's no issue with radicals to rationals. There's no variable in the denominator. There's no parentheses to resolve. We can jump directly into our derivative. And there's a lot of different notations for derivative. That's fine. Here, I start with y. So my derivative notation is y prime. And I'm going to go through power rule. So I'll take my exponent, bring that exponent down, and then subtract 1 from the exponent. So what does x to the 7th become? 7 x to the 6th. Yep. So we bring that 7 down, keep the x, subtract 1 from the exponent. Okay, part B, g of x equals cube root of x. Let's take the time to get it ready for power rule. So let's get that radical to go away. What's cube root of x? How can I rewrite that? X to the what? 1/3. There's a hidden 1, and we're always doing the 1 on the right divided by number on the left, x to the 1/3. So now I'm going to find g prime. G prime is equal to, let's go through power rule. That exponent is ready for us. Oh, and by the way, there's no other conditions that we have to worry about. Radical is good. Variable in the exponent is good. No parentheses, that's good. Okay, so g prime equals, bring the 1/3 down, x to the what? Negative 2/3, because you're subtracting 1. So 1/3 minus 1 is same thing as 1/3 minus 3/3, which is negative 2/3. I am going to ask you to clean up negative exponents. So we're going to resolve the negative exponent. We're going to push this x back down to the denominator. And I'm going to make it share the same space as that 3. I'm not going to be picky about how you leave your answer. You can leave your answer in rational form. You can leave it in radical form. I just don't want any negative exponents. So that's really the only thing there. If you want to write it like this, that's fine. Again, there's no need to rationalize your denominator. So any of these options are fine. Okay, part C. Rational, it's good, but what needs to be resolved before we jump into power rule? Yeah, that variable is in the wrong place. We cannot leave that denominator and say, oh, my derivative is just 4/5x to the fourth power. Okay, power rule is not going to, it can't be applied because that variable is in the numerator. So this rule is meant for variables in the numerator. And we don't have a rule for variable in the denominator. So we got to bring it up first before we do anything. So y is equal to 4x to the -5. Everything is set up and ready. Radicals, no issues there. Variables in the numerator, no parentheses. Okay, so y prime equals what? X to the -6. Part D, I'm going to change this problem a little bit. If you guys can put a 3 in front of 3 square root of x plus 0.875. Now, there are a lot of terms here, but the good thing is that as long as each term is nicely separated by plus or minus without any parentheses impacting them, you can treat each like an individual problem, and you can apply each rule separately for the individual. It's not like, oh, I gotta find one rule for all these terms. They're all individual terms. They're all individual problems. You can clean them up. Some of them may require more cleanup than others. But my strategy is in order for us to, it's easier to check your work if you just wait until everything is ready and just keep rewriting terms that are ready, even though it feels tedious. And then you can just do the derivative all at once. Because if you clean up one term and find the derivative of another, it's hard to go back and check, wait, did I do my derivative already? Or sometimes I see students do a second derivative because they didn't realize that they've already, they already found the derivative. So I'm just going to take the time to clean every term up. And once every term is ready, then I can just do my derivative for each of my terms. Okay, so first term, any issues here? This is ready to go. Yeah, right. This is no issues there, ready to go. I'm not going to make any changes. I'm just going to rewrite it and wait until every term is ready. Okay, the fifth root of x, this is not quite ready. How would you rewrite this? X to the 1/5. This is also not quite ready. There's two things we got to do here. That square root of x needs to turn into x to the what? 1/2, and it's still in the denominator, so we got to push it up and make it x to the what? -1/2. Now, what to do with that 3? That 3 is not going to come up. Okay, that 3 is going to be part of the coefficient. So I like to write this out this way: 2/3 x to the -1/2. And any time that I can move a number away from a variable, it just feels a little bit cleaner because I don't have to think about what to do with the denominator. So any denominator that's you can also always push it out as a coefficient. It just feels a little bit cleaner. It just feels like some number that's sitting in front of the x rather than a number that's sitting below. Okay, so I haven't done anything with derivative. I've just cleaned everything up, make sure that every term is ready for my derivative rule. So now I'll jump into my derivative. Y prime equals, okay, I'll bring the exponent down. Subtract 1 for the exponent. Okay, I'll clean this up later. Next term, 1/5 comes down. Subtract 1 from the exponent. 1/5 minus 5/5 is -4/5. Bring down the exponent. Subtract 1. So -1/2 minus 2/2 is -3/2. And then 0.875, this is a constant. What happens to a constant? Goes to a what? 0. Yeah. Imagine this is just some horizontal line that is hovering right below 1. And that horizontal line is always going to have a slope 0. So that's why the derivative is always 0. All right, let's clean this up here. 2 times 8 is 16, 16 over 3. I'm going to push this x down to the denominator, make it share the same space as that denominator that I have. So 16 over 3x to the 1/3. Next up, minus 1/5. I'm going to push that x down to the denominator, make it x to the 4/5. Negative 2 over 6 can reduce to be negative 1/3. I can also push this numerator x to the denominator. So I want to continue to remind you that the big picture here is that all we're doing is we're creating a very specified slope formula for these original functions. And so basically, if I want to find the steepness of any point on this graph, I'll just plug the x value into this derivative. If I want to find the slope behavior of this second graph, then I can just insert an x value into my derivative function, right? So every derivative function is tailor-made for its function because every function is going to have a different pattern, a different slope, different steepness. So every one of these is built specifically for the appropriate function that it's coming from. Okay, let's go to any questions, first page. Okay, let's go to the second page. Right? Example 2, if f of x equals 1 over x squared, find f prime of 2. So this is a two-step process. We're not going to do anything with 2 yet. First, you're going to find f prime of x. Okay, so we're going to find f prime of x first. And then once you find f prime, then you can insert 2 into the derivative function to get your slope. So first things first, we have to rewrite our function in the appropriate form to get it ready for power rule. So 1 over x squared, we want to write it as what? Guys, and if you're working ahead, I am making a change to number 4. So make that a 2 root x if you're working ahead. Okay, so f of x equals x to the negative 2. We got to find the derivative. F prime is negative 2x to the negative 3. Clean it up. Now we're clear to work on the slope. We want to find the slope of this original graph at x equals 2. So we simply make a substitution into our derivative function. Negative 2 over 8 reduces to be negative 1/4. All right, example 3. If the function is equal to cube root of x squared, write the tangent line equation to the function at x equals 1. So let's get this cleaned up. We're going to find the derivative. We're going to find the slope, but we're also going to find the ordered pair so that we can gather the ordered pair, gather the slope, then point slope form. Okay, so try those steps and we'll compare our answers. our function is x to the 2/3. We get it ready for power rule by converting that radical form to a rational form. So once we have our function settled, we can find the derivative. We bring the 2/3 down, subtract 1 from the exponent, do some cleanup, and then I'm ready to find the derivative. So I insert 1 into the derivative function, get it down to a number, and that number is going to correspond to the slope. But we still need to find our full order pair because they only give us the x value. So to find the y value, I'll insert 1 into the original function. So cube root of 1 squared, the same thing as 1 to the 2/3, which is 1. So there's my order pair. X, y value is 1 and 1. My slope is 2/3, point slope form. Any questions with 3? Okay, example 4. This feels more complicated because there's that denominator. Later this week, we're going to learn about something called quotient rule, which will handle derivatives for numerator and denominator of a function. But this, we can actually make it cleaner. That would otherwise be more difficult. And it's the fact that there's only one term in the denominator. So there's only one term in the denominator. That's nice because that will allow us to basically split up into 3 individual fractions. We'll clean up each fraction, get each ready for power rule, and there's no need for us to hold on to that denominator. We can handle that as 3 separate problems rather than just one. Now, as soon as I add more than one term to the denominator, then I'm stuck. Then I have to go through something more complicated, which we will learn later, called quotient rule. But here, this is not 2 root x plus 1. This is just 2 root x. That's just a monomial here. So we can split up into individual fractions, and there's no need for us to treat this like one big problem. We can split this into 3 smaller problems. Okay, so let me kind of show you what that can look like. Okay, so I'm just going to rewrite every numerator and denominator. I'm going to kind of clean things up along the way. I'm going to convert radicals to rationals along the way. And then that 2 root x is really 2x to the 1/2. So I'm just writing it 3 times, once for each numerator. So cube root of x is x to the 1/3. So now I'm just treating these like 3 separate problems. Now, even within these 3 individual terms, even though we're targeting power rule 3 times, 1 for each of these terms are still not ready. Okay. What's out of place still in order for us to do power rule? Denominator. So I got to bring that denominator up, and this denominator can come up as x to the what? X to the negative 1/2. And if I have 2 bases next to each other, I'm going to be adding their exponents. In this case, we're thinking of it as subtracting because this is going to come up as x to the negative 1/2. So 4 minus 1/2 is just going to be 8 over 2 minus 1 over 2, which is 7 over 2. Or you can think of it this way. You can just think of it as, okay, if I have bases above each other, I can just subtract the exponents. So 4 minus 1/2 is 8 over 2 minus 1 over 2. 2 minus 1/2 is 4 over 2 minus 1 over 2. And then 1/3 minus 1/2 is 2 over 6 minus 3 over 6, which is negative 1/6. And then all along the way, I'm also pushing out the fractions in front And that way it'll just feel like a very clean power rule because it'll look exactly like how other terms are, where my number is in front. There's no number sticking out below my variable. It's not wrong. It just feels a lot cleaner if you don't have to if you don't have to look at a number below the variable. Okay. Now we haven't done anything with derivative. All we've done is we just put it in a different form that's more conducive for power rule. Now we can go through power rule. So now we can bring each of the exponents down, subtract one from the exponent, and we can also rename that f of x. Now we've turned it into a different function. We've turned it into a derivative function. So technically, this is the correct answer, but we can do some cleanup, and I want you to do some cleanup. So any coefficients you can put together, any radicals or any negative exponents that you have to resolve it by pushing that variable to the other side. And you can leave your answer in radical form or rational form. For me, it's just easier to leave it in rational form, but if you want to convert it back to radical form, it's up to your preference. Okay. But for me, I just prefer to write it in rational form, but it's up to you. Okay. Any questions? All right, example 5. Find f prime if our function is 3x times x plus 1 squared. We want to go through power rule, but what's standing in the way? Parentheses, yeah. So anytime your variables are connected together by multiplication, either through parentheses or if you have variables that are next to each other, like x times x to the 1/2, we can't do power rule until all the multiplication things are resolved. So in this case, if you see parentheses in the way, that's usually an indication that, okay, I can't just jump to power rule. There are other rules available, which we're going to talk about later, like quotient, chain, and product. But sometimes a problem is easy enough for us to just expand first, just rely on power rule. This is one of those. So just make sure that you're expanding in the correct way. We can't distribute the 3x through. You got to take the time to expand out your binomial. So make sure you write your x plus 1 twice, expand it out, then distribute the 3x. And then once each term is nicely separated with no more parentheses, then each term can get the power rule treatment. So I like to write that x plus 1 out twice as a reminder so that I'm not accidentally doing x squared plus 1 squared, because that's not enough, right? You got to take the time to FOIL out create a trinomial, and then that 3x can distribute. But keep in mind, we haven't done anything with calculus yet. All we've done is we just cleaned it up so that we can actually step through power rule. So now it should be pretty straightforward. Power rule. Okay, any questions here? Okay, you guys have quite a bit of homework, so if you guys can start on your homework, I will put the key up here so that you guys can see for the first few problems and you guys can kind of work through. So check your calendar, page 190 to 193. You guys have 15 minutes, so see how much you can get done and the rest you will be able to finish up. Well, feature, maybe it's a further problem that I'm not showing yet on the board. Ask me that.
Hey guys, come up and get your phones.
What did you get?
So
I actually put.
Like my character, I just wrote it down on this. And then this was. On the chat. It's all one. We didn't express it all. I would.